Okay, so in this talk, I will talk about the VLSI architecture for communication signal processing. So the talk is part 1 and part 2. Usually at some venues I gave like almost 3 hours, some venues I gave 2 hours. So it's a long talk, but what I will do is I will try to compress into 1 hour. So what I will do is I will go more go a little bit more on the basics, and then I would spend a little bit more time on the LDPC and turbo equalization, and then based on how you feel it, I can basically pace myself. I have a lot of slides in the backup, so I can go into the different details as needed. So the part 1, I would go over the basics and then talk about pipelining and parallel processing, and then folding, unfolding, retiming, systolic architecture design. On part 2, I talk about the LDPC decoder and turbo equalization and a new interleaver called local global interleaver and the queuing. And then the two advanced topics are the error flow mitigation and the TMS. Those probably I would just mention that of what they are. So in terms of the problem, most of people, I assume that some of the people work on the DSP. So usually when you implement a DSP algorithm, you don't take the algorithm directly as it is. You basically try to see how can I modify this algorithm to get the same SNR performance? Can I modify the algorithm? It doesn't need to be the same equation, but it could be a modified equation, or it could be altogether a new algorithm. Can I implement this? Can I get the same performance by modifying the algorithm so that I can have less computations and less memory? Because eventually it has to end up in silicon. Or even if you're doing on a processor, because you want to spend less execution time, even if you're implementing in a DSP or a general purpose processor. So that's what we have to do in terms of, we start with the base data processing algorithm, simulate in C or MATLAB, and then try to see what is the most hardware friendly algorithm. So for this one, you need to have understanding of both the algorithm complexity as well as how it translates into the hardware. And then usually it's an iterative process. Right now the humans are best in this one, even though they claim that so there are some tools, but those tools are mainly for, okay, already humans developed, okay, if I have a filter structure, can I modify my data flow graph in a different way, and then this data flow graph is efficient, the humans proved it, and then the tools can say that, okay, once they recognize the original filter format, they can convert into whatever the format that is needed for the one. So essentially tools are essentially following our human instructions. So humans are still best in this one right now. And then another one is the time to design is increasingly an important factor. And this, I think some of people probably might have been working in Qualcomm. So the reason the Qualcomm has a lot of design wins in Snapdragon compared to the other processors, so say for instance NVIDIA mobile processor Tegra. I worked at Tegra because that's a very powerful one. But the problem is we didn't have the modem in time integrated. So we have a separate chip, and we integrated, but it's too late. So essentially, time to market is very important. And so in terms of the basic ideas, I think most of you are familiar with the parallel processing and pipelining. So is basically, you have a base design. Say for instance, I'm operating at 0.5 gigahertz, 500 megahertz. It's a 2 nanosecond cycle time. So I have two operations that I want to do, A and B. These could be any operation. This could be like a addition or subtraction or multiplication and so on. So now basically if I want to have, instead of getting at 500 megahertz, can I do it faster? So I can process more samples per second by putting two parallel paths. So that's essentially a parallel processing. If these two operations are independent, then I can do the parallel processing. But if there is a dependency between the operations, then you cannot do parallel processing. So in the pipeline, what you're doing is, instead of trying to do the two separate hardware paths, you're trying to speed up the path, like speed up the operation, like how much critical, what is the critical path, like can you reduce the critical path from, say for instance, 2 nanoseconds to 1 nanoseconds. So you're spending more time in terms of the pipelining here. So there are different trade-offs in terms of the parallelization and pipelining. So usually what we have is, in terms of the parallelization, you can see that there is an area of overhead here. So essentially you're almost duplicating another path. And here pipeline, there is a less area of overhead, but sometimes there is a choice that you need to make. If you are worried about the power consumption, people, what they're making the choice is, okay, it's better for me, rather than pushing the frequency, let me put two parallel paths. That basically helps in the power. And if I'm concerned more about the area, I would say that okay, I can do 1 gigahertz easily at 28 nanometer. Let me push until 1 gigahertz. But beyond 1 gigahertz, if I want to push more, I probably don't push beyond 1 gigahertz in 28 nanometer for any ASIC. Then I would go for the parallelization. So it's a usually trade-off. So usually in the pipelining, essentially, if you can think of it as an operation, say for instance, you're doing, let's say, 3 multiplications. It's a very simple example. So the samples are coming, and then you're computing the y of 0 as the multiplication of the 3 input samples. So you're doing essentially these operations, operation A, B, and C. So essentially, if you see in the pipelining, so they have the essentially dependencies between those operations, and what is happening is here is, even though you're reducing the critical path, you are basically, like, in terms of the latency, in terms of the clock cycles, you're introducing the latency. Then another issue is there with the pipelining is, like, when we are adding these flops add a considerable delay on itself, like setup time and so on. So the pipelining is not doesn't solve all the problems, because you cannot keep on adding the flops as many as you want. There is always a limit in terms of, because as long as say for instance, if this flop doesn't add more than 5% overhead in terms of the timing budget, that's okay. But if it is adding, let's say, like a 20% or 25% overhead, it may not be that good. So in terms of the one example I alluded before for the filter, say for instance, you have this filter equation. So this is essentially like an FIR filter. So you have the different samples that are coming in. Say for instance, here you have like 2 delayed versions of the input sample, and then you have 3 multiplications, and then there are 2 multiply and accumulates here. So now in terms of the signal flow graph, you can represent this way. So you have x of n, and we are representing this delay here. Now if you see that, if I want to see what is my critical path on this one, so I need to count count my critical path based on this one where there are no delays here. So here if I see that I have one MAC here I'm doing and another MAC I'm doing, so essentially this is the bottleneck. So essentially what would happen is, like, if I'm using, say for instance, a mth order filter, what would happen is I need to do basically log to m additions here if I'm using tree adders, and then there is a multiplication delay here. So if you take this example, say for instance, the critical path for this is a multiplier delay, and added with the two adder delays if you're doing a serial adder. But what if you're doing a parallel adder? So that would be essentially like one adder delay and then one multiplier delay. So now what if you do the transformation on the signal flow graph? So the original signal flow graph is this. Now what you can do is you can basically, we're first of all changing the direction of the direction of all the edges. So instead of going this way, we're changing this way, and then at the same time we are changing the input and output. So the transformation is the output result is exactly the same. Now if you see this, what we have here, so essentially this is a redrawn figure of this. So if you see this one, now if I am looking for the critical path for this one, this doesn't depend on the order of the filter. This only depends on the critical path is only like one adder delay and plus one multiplication delay. So essentially you changed a signal flow graph, and then you said that okay, the critical path is no longer depends on the order of the filter. So this is one thing what we use in the filters. So then another example I want to go through is usually what we want to do is whenever we are writing equations for the DSP, we always want to write in terms of the equations and matrices. Why we want to do in matrices? Because there is so much rich theory developed in matrices. Now if I want to do a matrix inversion, I can basically rely on all the theory that was developed in terms of the matrices, and I can analyze if my matrix satisfies some of the matrix properties. Now I can invoke different theories to simplify those computations. So we always try to represent the operations in the matrix equation. So this one, what we have is here is again an FIR filter. So here what I'm writing is in terms of I'm processing essentially 3 samples at the same time. So I'm writing essentially instead of n here I put 3k, and then substituted 3k everywhere I find n. Now if because I'm interested in computing 3 samples, I have y of 3k, 3k plus 1 and 3k plus 2. So if I'm interested in 4 samples, it would be 4k, 4k plus 1, 4k plus 2 and 4k plus 3. So now if I define my block vector as this, now essentially my y of k would be like essentially it would be in the matrix format this way. So now again, this example, what I'm trying to get is if you write in terms of a block matrix formulation, then you can use the matrix properties to simplify your computations. You have much more better formal framework. And again, this is another concept we use in the signal processing. So you have, say, for instance, two operations that are doing on two different data paths. And now instead of doing two different data paths, what I can do is to save the arrays, I can multiplex. Essentially, it's a time sharing basically. So I put a multiplexer here and I'm doing the same operation here. And so here, what I'm doing is previously it was operating at 1 gigahertz. Now I bumped up the frequency of this block to 2 gigahertz, and I'm getting the essentially the same throughput as this one. Now another way I can do is I can multiplex for the same speed of this original block, but I need to operate the two input streams at a slower frequency. So the effective throughput is basically reduced. So you can do, if you want the more throughput, you can basically bump up the frequency, or if you are like okay with the effective throughput, you can basically keep the same frequency on the block. And another concept we use is the folding. So basically the folding is, let's say it's more, you can think of as iterations. Let's say in most of the signal processing, you do multiple iterations. Let's say if you have to do 5 iterations, now instead of doing 5 iteration blocks, you can just have one block, and that block repeats the same operation multiple times. Usually what happens is the iteration is usually not the same iteration. Usually what you want to do is you want to formulate your iteration as that depends on some parameters. So you need to formalize that, and then you can do this folding operation. So sometimes what I'm meant to say is it's not always straightforward how to fold the operation, because they look different. Sometimes each iteration may process differently. But if you formulate your problem correctly, each iteration could be parameterized. There is the same iteration with different input parameters. And then unfolding is another one. So unfolding is nothing but let's say for instance the opposite of the folding. Now in this example you have an IR filter here. So what we are doing here is, here I can compute only one output sample per clock, but now I am asked to compute two output samples per clock. So what I'm doing is this equation, remember the previous one, I said if I want 3 samples, I start with 3k, 3k plus 1 and so on. So here I want 2 samples, so I started with 2k and 2k plus 1. So simply I substituted this one. So what is happening here, so if you see this one, 2k plus 1 minus 10, so essentially, instead of this 10 delay, because I'm operating at 2 samples per second, this 10 essentially becomes 5 delays here. And similarly, instead of 8 here, this one becomes a 4 delays. So now you have a different data flow graph that you can compute 2 output samples. And so now another simple concept we use is the retiming. So retiming is nothing but, let's say you have 3 inputs that are coming and you have delays on here. Now you don't necessarily need to do the delays on the inputs. You can do the delays on this output block also. And similarly, you can move the delay to this one. Now where you want to do the this delay, that depends on your trade-off basically, like whether you want to worry about the essentially the area occupied by the registers, or the speed of speed of these modules. And so basically I went over very quickly on this part one, but basically the concepts are very simple in terms of the DSP, the basic concept. But the problem comes in when you look at a complex algorithm. There are so many things that you don't know what path you want to do the folding operation, what part you want to do the unfolding, and what part you want to do the parallelization, what part you want to do the pipelining. Because the main requirement is you want to do the we want to have a less area and less memory. So when you look at a very complex mathematical formula, it is not very clear how you want to do those operations, how you want to sequence those operations, whether you want to change those operations or not. But the fundamental concepts are simple. The complexity comes from the fact that the algorithms, the underlying equations that you need to do for a given algorithm are more complex. So any questions at this point? I think I went over very fast.
I had a question.
Yes.
It actually goes back to the very first one where you were showing the change in direction of the processing of a filter. I think it might have been the first or second slide if you want to find it. Anyway, and I didn't get that. drawing the arrows in the opposite direction. Yeah.
Okay, okay. So you're saying that how we got this transformation?
What's the relevance of drawing it backwards? I didn't get that.
Okay, okay. So basically, what we are doing here is if you look at the original one and this one. So essentially, what we are doing is instead of the delays on the top line here, if you do the do the reversing of this one, you are seeing the delays on this one, right? So now when you look at the critical path, since you have the delay elements, you don't need to count the critical path. Like basically, the critical path is computed between the delay elements. So essentially, the critical path is reduced.
I don't know what you're doing in the second diagram. You're just drawing it in reverse, so I don't know the significance.
Okay, in the second step, what I'm doing is I changed the. So essentially, right. So I have, say for instance, I have an operation that I'm doing as a y of n is x of n plus x of n minus 1. So essentially I represented that equation here. Now what I'm saying is I can represent the same equation by changing the output to the input and by changing the direction of the edges.
Isn't that another way of saying that if you have a minimum delay per filter or a maximum delay per filter, they're related by the coefficients flipping?
Yes, yeah, yeah.
So it all depends on how the per filter is structured.
Yes, yeah, yeah. So it's the same equation, but you are basically like the internal computations you are doing in a different sequence. So here, say for instance, this one what we are doing is we are essentially buffering the inputs, right? So here what we are doing is we are not buffering the inputs. We are, whenever an input sample comes in, we are multiplying that x of n with all the coefficients, and then we are storing them in the registers. So these registers weight is increased as compared to here, but that is not clear in this figure. But here we are only buffering the x of n. Here we are buffering the x of n multiplied by the coefficients. So what we are saying is if I have so I can write it here briefly here. So basically, okay, oh, okay.
All right, just to clarify for myself. So first of all, the circles represent delay elements plus multipliers and.
The circles represent the multiplications. D represents the delay. So I think here, give me 1 second here. So this one represents. Sorry, I think this is not clear here. This should be an adder here. This one, and the top one is essentially a multiplier here. So I think this is probably more appropriate actually. So these top ones are the multiplier. These ones are the addition bottom ones.
So you can do it in reverse. Okay, I guess the picture on the right is clear at the bottom. So, and you're saying you can do this in reverse and.
Yeah, so basically let me explain here. So here what we're doing is we're taking the input and then we're multiplying with all the coefficients and then we are storing those intermediate ones in the delays. Yes, it's a standard transformation, yeah.
So what are you going to do to speed it up?
Okay, so what we are saying is if you do the original one, let me see whether I have a original one here. So the original one is here, right? So what I have is I have the x of n and I'm buffering those x of n's, right? And then now I'm doing the multiplications on those.
Right.
Now what I'm saying is if I use this structure, my critical path depends on the filter order. Because the critical path is essentially this multiplier and these two additions.
Okay, well.
But if I do do this kind of structure, then my critical path doesn't depend on the order of the filter.
Close enough to
Okay, we can address it offline.
There are many ways to implement the per filter.
Yes, yeah.
So is that involve different the other? I forget how those are called. The first two different bases.
There is a direct form 1, direct form 2. There are different forms. Basically, what I'm saying, I showed one realization in which the critical path is independent of the filter order.
I'm sorry.
Okay. So in the part 2, I talk about the LDPC and turbo equalization. This one I probably would go a little bit slow on the concepts for the LDPC. And
What does LVPC stand for?
yes, I'll go for that. Yeah. So basically, let me see. I think probably okay. Before going there, so LDPC is a low density parity check. So if you're familiar with the Hamming code, if you represent in terms of a parity check matrix, those equations you can represent as part of as part of a matrix. So that what we call as a parity check matrix. Now what we're saying is LDPC is also a parity check matrix, but the number of ones in that matrix are sparse. So that's where the term the low density comes from. So the number of ones in matrix dictates the complexity of the decoding, because the more number of ones are there, the more processing you have to do.
So just very high level, it's a form of forward error correction. So it'll be like you'll read Solomon, convolutional code, more recently turbo code.
You should say
Viterbi well, Viterbi is the decoder.
Yeah.
That's the decoder.
Yeah, it's a decoder for convolutional code even.
Well, this is an encoder. Encoder. LDC is a code, so that's what you encode it.
Yes.
And so it's for correcting errors. You add extra parity bits, and you use those parity bits later on to correct errors in the block or whatever it is, in the data.
So I'm stepping a little bit out of order here to this slide. So you can have, let's say for instance, a random code. So random code is nothing but you generate a random code and you use a lookup table to decode it. But the complexity is more. You cannot decode really more than, let's say for instance, like 16 bits or 24 bits, because the lookup table size is essentially exponential. And so for the Shannon random code, you can have a 0 dB to achieve 1e minus 5 for the rate of code. The rate of code means you are putting a 50% redundancy. Now for the BCH, you need 5.4 dB. For convolutional code, you need 4.5. And then iterative turbo code, you need 0.7 dB. Now LDPC is basically a little bit better than a turbo, but it's basically close to 0.0045 dB. And so the difference is essentially in terms of the turbo and LDPC. So LDPC, you can have a lower complexity compared to the turbo. That's one advantage. Another advantage for the storage especially is the turbo starts to have a severe error flow issue, basically after 1e minus 6 or so. In the wireless, you really don't need to worry about error flow, because wireless, the required bit error rates are typically 1e minus 5, 1e minus 6. But in the storage, the bit error rates we really want is 1e minus 14, 1e minus 15. Because if you write something to your the hard disk drive or the SSD, you want to be able to read it back again. Because in the wireless, you have the retransmit. We don't have that luxury in the storage. So we considered both the turbo as well as LDPC, but turbo, the error flow issue is severe. LDPC also has error flow issue, but we have the solutions for that. For turbo, the error flow solutions are not that good. So let me go back to this one. So essentially, what are the channel impairments and the requirements for the HDD to begin with? So data rates are usually 3 to 5 Gbps. So 3 Gbps is typically for a notebook hard disk drive. 5 Gbps usually for a desktop and the enterprise. And the real-time bit error rate requirement is 1e minus 10 to 1e minus 12. So real-time means when we read the data from the hard disk drive, when it is operating at this line rate, that errors you should see should be around 1e minus 10 to 1e minus 12. And the quasi real time, that means I occasionally get some error, but I can do some post processing that affects my throughput, but that happens very rarely. So I need to achieve 1e minus 15 to 1e minus 18. And what are the main channel impairments? ISI, I think we talked just a little bit before. So there is an intersymbol interference, and there is a data dependent noise, that's jitter. And then we have the erasers. So erasers is nothing but, okay, that's part of the data. Let's say if you think about a simple example, you touched these, for instance, media, let's say for instance a CD, that essentially erases all the data there. So what we do is we put the interleaver so that whatever the data that is erased there, it doesn't happen to be a continuous data for the decoder. It happens to be a random data for the decoder. So then the decoder can correct it. We'll talk a little bit more on the interleaver briefly.
ISI is intersymbol interference. Is that
yes, yeah. And for the flash is basically the data rates are 0.3 to 5 gigabytes per second, so it's almost like 8 times more. And then the similar bit error rate requirements has hard disk drives, and the channel impairments are not that bad as the hard disk drive. It's not basically signal processing wise, it's very in the hard disk drive we have a preamplifier, analog front end, and turbo equalization. The flash, the channel is very simple. We read from the flash like a threshold voltage, whether that threshold, whether the red voltage is below a threshold voltage or not. That's a hard decision. Sometimes if you read it multiple times, or if you read a soft information, you get some voltage level, but that's pretty much it. And after that, you need to do some signal processing, because say for instance, this is a MLC in which there are 4 levels. So these are the ideal ones, the blue ones are, but the actual ones could be shifting over the time, and also could be due to the program error cycles. So if I write, let's say 300 program error cycles, there could be some shift. If I write 3000 PE cycles, there could be more shift. That means originally what I was thinking about this reference 1 and reference 2, they're no longer valid. I had to change those references as well as I go on. So I had to learn what should be my reference voltages to compare with. And similarly, when I'm doing a soft decision, I would be doing multiple comparisons with the multiple reference voltages. So that means those levels also have to be shifted. So there is some signal processing involved there to determine what has to be done. But in terms of the signal processing complexity, it is much easier, because essentially what you're doing is you're estimating the histograms. And but in the hard disk drive, there is a lot more signal processing. But then once you do the signal processing in the flash, then pretty much you can use the ECC. Right now, all the products that are shipping has a BCH, and we're considering the LDPC.
So I would just, I think based on my conversation, I'd really maybe take an extra time to explain the source of the ISI in the disk and the type of interference. I would just think maybe a little longer. For example, my understanding is that
yeah. So I have
the flash RAM will deteriorate.
Yes, yeah.
And you will get more intersymbol interference.
The intercell interference
later on.
Yes, yeah.
Is what I've read.
Yeah, I don't think I have the slides on that one, but I have some slide on the transition jitter for the how that happens in the HDD. So usually when you write on a plate of that magnetic recording, you have essentially like what we have is essentially there's a kind of these pockets of grains, and you need at least 100 or more to record as a magnetization as 1 or 0. And so now what happens is, because these are not exactly like basically it's not an exact transition. You can do a bit pattern media to do the exact one, but that is very expensive. So right now it's still like you do the regular one, you write it like without any pattern media. Now since this transition boundary changing, so basically like what you read is essentially impacted by the neighboring cells. Essentially, this is what the hard disk drive. So essentially, this is what like happens as a transition jitter. So essentially, this is a data dependent noise, because what you read in one pocket depends on the other pockets. And now for the wireless, I think most of you are probably are familiar. So the data rates are actually much lower, but right now they're catching up with that. But even the highest one is around 1.3 Gbps, and so the real-time bit error rate, as I talked, is 1e minus 6. It's much like relaxed, because you have a retransmit. And the main channel impairments are the ISI. The ISI comes from the frequency selective channel now. So this is not a data dependency. There is no data dependency in this ISI, and then we have a time varying fading channel and space selective channel and deep fades. So basically for the wireless, actually in one sense, the algorithms we use are actually more complex for the MIMO as compared to the hard disk drive. The hard disk drive complexity is only just the turbo equalization, right? But here, like in the MIMO, because you have much more complexity even before doing a turbo equalization. So there are more digital signal processing algorithms you have to do. But in the hard disk drive, the signal processing you have to do is pretty much has to deal with the doing some analog equalization, doing some DFE and so on. But in the case of wireless, you have a lot more things that you need to do. And then essentially what I'm saying here is, for ISI channels, whether it's a wireless or the storage, the near optimal solution is you can use a turbo equalization, a detector and ECC. For the wireless, if you are using a MIMO, use a spear detector. And if you use spear detector combined with LDPC and then you iterate it, then you get much better gains. But the spear detector itself is a complex animal, and LDPC itself is a complex one. And then if you ask the companies to iterate, okay, they will say, okay, we will consider later. So, but I think at some point of time that's possible, because right now there are more academic papers on the turbo equation for the wireless, but it's going to happen. And so for the wireless, basically you probably you seen the less if you're traveling in the car, and basically if you're getting a signal, that signal is going to bounce from different paths, and when you receive it, it could like add up constructively, or it could basically like cancel each other. But that cancellation and add up is going to change with the time, because as you're traveling, your reflections, your essentially these reflection environment is not the same. And so typically what you see is, say for instance, this is in time in milliseconds, this is how your channel is behaving. So the channel would have a different different gain each based on the time basically. So it has a SNR variation. So that's the fading what we have. So so now what you can do is to do the errors. So basically this is a very basic block diagram of a communication system. You have an information source. So this information source could be a text file or could be an image. And so what we're doing is we're doing a source encoding. So source encoding is if it is a text file that has an ASCII data, right? So instead of representing the whole thing, so you can do a JIP algorithm. So you can try to remove the redundancy. And if you have an image, you can do the JPEG. And if you have a video, you can do the MPEG. So essentially what we're trying to do is we're trying to compress the data as much as possible. And then what we're doing is we're introducing the redundancy in the channel encoding. So the reason we're introducing the redundancy in a controlled manner is, if there are errors, we want to be able to recover from those errors. But we don't. But the question could come like, we just removed the redundancy, we're adding back the redundancy, but we're not adding the same redundancy back, but we're adding the redundancy based on mathematical formulae. So because previously the redundancy that is there in the information source, that is not defined by any mathematical equation. There is a redundancy, and then we use some mathematical equations to remove the redundancy. But in the channel encoder, we are like adding the redundancy using a different set of mathematical equations. And then we have the digital modulator. So the reason the modulator is needed, you cannot simply put ones and zeros into the air or into the wire. So you need an analog waveform. So before doing the analog waveform, you need to basically like do the required modulation scheme, like either a QPSK or a OFDM, and then do the basically the D to A conversion. And now on the receiving side, you have a digital demodulator, the inverse of the modulator, and then the channel decoder. So this is basically like we're doing the error correction decoding, and then you have a source decoder. It's like kind of, you can think of as an MPEG decoder or the JPEG decoder. So in terms of the channel encoding, the best scheme that is available right now is the low density parity check. I will briefly talk about this one. So I think I talked about this slide already. So essentially what is available for right now in terms of the channel capacity. So the channel capacity mean for a given bit error rate, which code requires the minimum SNR. So for that question, so LDPC can achieve the one. So right now recently there are some codes like similar to the LDPC, those are called polar codes. But the complexity of those codes are higher than the implementation complexity of those codes are higher than the LDPC codes. So polar codes comes from the fact that you basically like that basically operates more on the you can think of as a decoding is a successive cancellation. So it's a different kind of algorithm for that. But you have the similar gains as LDPC, but the like in one way it is not still implementable. So that's one future research area if anybody wants to work on that. So more on this one, these are introduced, the LDPC codes are introduced by Gelazer in 60s. And then in 90s, again, there is a lot of interest after turbo codes were reinvented. And then a lot of people worked on that, like at several universities, and happened to be one of the people who started working on the implementation at Texas A&M. And then it helped out that I continued that work at it's almost like doing as a postdoc at different companies, like at Marvel and VLSI. So the simple concept for the ECC is this. So you have these 4-bit messages. So you have 16 combinations. And now instead of transmitting these 16 combinations directly, what we're doing is instead of transmitting 4 zeros, we're adding 3 more zeros here. And instead of transmitting this 1 0 0 0, we're transmitting this sequence here. So we're adding a redundancy, but this redundancy is based on a mathematical equation. Now what happens is, if say for instance we transmitted this one, the all zero code word, but what if we received the another word here? Now this 001, this is not a valid code word in this. So you know for sure that there is an error. What you do is you compute the Hamming distance between the received code word and all the possible code words. Now what you do is you compute the after computing the Hamming distance, you select the code word which has the minimum Hamming distance between the received code word and the possible code words. So in this case, the all zero code word has a minimum Hamming distance, because if you see the other codes, this one has like 4 flips required for this one. So that if the Hamming distance, let's say, you can simply XOR this one, the received code word, with the valid code word here. So there are 4 flips are needed. If I transmit, let's say for instance, this sequence 110100, then in order for that sequence to change to this one, there are 4 bit flips needed. So what we say that, okay, since if I transmit the sequence, there should have been only 1 bit should have been flipped, the probability of one bit getting flipped is much higher than all the 4 bits getting flipped. So this is a crude one. So essentially we have a list, and then we are doing essentially computing the Hamming distance, and essentially we are doing all the possible combinations. But in reality, we do more sophisticated decoding. So for LDPC, what would happen is, let me see how much time I am. Okay, yeah, good. So basically what happens is you have the H matrix, that's a parity check matrix. So what you have is variable nodes and check nodes. So essentially, like for instance, in this one, you have an example here. So what we are saying is V2 plus V4 has to be 0. So what it means is, here I'm transmitting only 1 bit, but I'm adding almost 5 more bits of redundancy. And so what I'm saying is, whenever I transmit my bits, my V2 plus V4 should add up to 0. So if my V2 happen to be 1, my V4 should be 1. If my V2 is 0, my V4 also should be 0. So basically I'm putting some constraints on the transmitted data. So is it clear? Is the slide clear at this point? So basically what I'm saying is, these are the different parity check equations. The first equation is V2 plus V4 is 0. The second equation is V1 plus V2 plus V4 is 0.
I'll ask a question, and I'm kind of being a wise guy, but what's the code rate of that code?
This is 1 by 5 basically. Like there is
so
one.
You send 1 bit, and there is no code rate because you haven't specified the parity and the data.
No, you can basically see that there is a 5. Actually, it's a 5 by 6, like one by 6.
Where's the data? Where's the parity? If I encode that, how do I encode
No, it's a 1 by 6. So basically, you have 6 data bits you're transmitting, and then 5 parity bits. So essentially, for every 1 bit, you're adding 5 parity bits. This is a very simple example. So essentially,
this is 6 by 11.
Not 6 by 11. So it's basically like the data rate is for every 1 bit you're transmitting 6 bits. It's a 1 by 6.
So it's rate 6 code?
Yeah.
I don't think it's any rate because you haven't specified what it is.
No. Basically,
you could say it's a 4 by 6. You could say it's a 3 by 6.
No. Because
that's not the generator matrix. You need to give me the generator matrix. That's
no. You can get the generator matrix from the H matrix. So basically, right, what we are saying is the H1 matrix, the number of columns is the number of bits that are transmitted.
Correct.
So now what you're saying is, the number of bits we're transmitting is a 6, right? The number of parity bits we introduced are equal to the number of rows.
No, but you didn't transmit those, so those aren't the bits. You can make that a 4 by 6. It's a 6. The encoded block is 6 bits.
Yeah, encoded block is 6 bits. Yeah.
The data and the parity is arbitrary. You can decide what the data is.
Yeah, but what I'm saying is here the parity is only the 5 bits. So there is only one data item there.
I just think it's an oddity with LDPCs that you describe with parity check matrix because it doesn't define the code. But anyways,
okay, but this parity, right, is basically valid. It doesn't need to be an LDPC matrix. It's a parity check matrix. So what I'm saying is, this parity check matrix is a valid parity check matrix. So this is essentially adding 5 bits of redundancy to 1 bit of transmit.
Look at the diagram.
So why don't we return to this later? Because I think
yes, yeah. So basically here the way the relations are described, what we are saying is this S1 to S5 or the syndrome check. So these are the equations that we are saying that okay, these equations have to be satisfied for the transmitted bit. So essentially this V1 to V6 are the transmitted bits, and now those transmitted bits have to satisfy these parity check equations. Like one thing I said, S1 is V2 plus V4, S2 is V1 plus V2 plus V4, and so on.
Are you familiar with the DBBS2 LDPC code?
Yes, yes, yeah.
So what is the H metrics? What is the size, just the size of the H metric?
It is around
The H
60.
matrix.
Yeah, it's around
or
64K or something. Yeah.
It's by what? By what? 64. It's 6400 by something.
It has different rates basically, and also the circulant size is 360.
For the rate 2/3. Could be, wow, the math is easy.
Yeah, it's basically like a 6. Yeah.
Okay, but you see, you have to know the parity and the data. But when you just give me an H matrix, it doesn't tell me.
No, you can always get a. Okay, that's what I think. That's the confusion.
Because it's the same size, exactly. It's the same size matrix for every one. It's a 64.
No, I think you're getting it wrong. I think one thing I would say, we never need to use, let me say one thing. We've done several encoders and several decoders. You don't need to do a generator matrix to do the encoding. You can do the encoding using the H matrix itself. So there is no real need of the generator matrix.
But I don't know the code yet, because I don't know how many bits I get to put in and how many parities.
No, I think you are missing the definition of the H matrix. The H matrix is defined that the rate of the code, you can say that the number of bits.
We lost the video.
Okay.
This is strange. I've never seen this happen before.
You know, for the rest of us, you'll have to do a little example.
Yes, yeah.
for How this code is constructed. and how it's transferred.
This has never happened before.
We can get the slides back, we can do it now.
Just suddenly stopped. Are you on with power? Continue. I think that's what the story is there. Can we just continue with the lecture, please?
Yes. But is it coming on this one?
It could be enough if you're not gonna do anything.
Okay.
I'm saying, I don't know. That
Where is shoe?
I don't know why
that's
we don't use these. It's all about recording. But
Okay, it's
that's
coming up.
the
Yeah,
problem,
it's coming
yes.
up. Yeah.
Can we do the questions later, please?
Sure.
Okay. Okay. Give me 1 second. I just want to make sure it's okay. Continue recording. Okay, so basically on this topic, the H matrix, take my word, basically the number of the bits that are transmitted are equal to the number of columns in the H matrix, and the number of parities that are introduced are equal to the number of rows. Now you can do the shortening, you can do different things, but basically the definition of the parity check matrix is this is how you are doing. You can do the encoding using the parity check matrix itself. So basically when you have the parity check matrix, you can basically, once you define the rows and columns, you can basically do the encoding such that you're adding those five more checks basically. And now in terms of the decoding, the way it happens is you have the V1 to V6 and then the different syndromes. So what we do in the check node updated is nothing but we are computing these syndromes. Say for instance this V2 plus V4, we are evaluating what is the result of that, and similarly V1 plus V2 V4, we are evaluating that one. And now what we are doing is, after this syndromes got evaluated, what we are doing is we are going to change some of these bits based on the syndrome. So let's say if the syndrome is not satisfied, this V2 plus V4 is not satisfied, let's say V2 happened to be 1 and V4 happened to be 0. Now you could flip the V2 to either 0 or you could flip the V4 so that the resulting equation is satisfied, right? So let me show one example here. Say for instance, this is one parity check matrix. Is like the same example as before. So what we are saying is like essentially each bit is representing is essentially a connection between the variable node and the check node. So you have these check nodes, the red squares, and then you have these circles. Those represent the variable bits. These are the encoded bits. So you have a total of 6 encoded bits, and you have total of 5 check nodes. And then when you are encoding, you encode such that the parity check constraints are all 0. So that means this parity check is composed of the bit like V1 plus V4 that should add up to 0. So that is what it is adding up. So there is a 1 and 1, the both added together. That's a GF2 addition. That's a simple XOR operation for the binary LDPC. So it becomes a 0. Similarly for this parity check, so you have the 0, 1 and 1. So again, all these 3 would add up to 0. So essentially when you are transmitting, you made sure that the bits are such that you satisfied the all the parity check constraints as 0. Now say for instance you received the like instead of receiving say for instance like this 0 1 0 1 1 0, you received an error on this point. So you have this essentially like instead of 0 1 on these first 2 bits you received 1 0. So there are 2 errors you received in these 6 bits. Now if you if you compute the syndromes, right, what would happen is the first syndrome happens to be 1 because this is 0 and 1, 0 plus 1 is 1, and this one is 0. This is still satisfied even though there is a bit in error here. And the reason this is satisfied because there are 2 bits in error, so this parity is still satisfied. And now if you look at this parity again, this is not satisfied, there is an error here. And now what you can do is you can see like what bit to flip. Again, this is a very crude decoding. This is what we use in practice. We use more sophisticated decoding algorithm, but this is more in terms of the if you are using a bit flip decoding or hard decision decoding, this is how you can do it. Now in the first step, what we do is essentially, as I said, we have an expected message and a received message, and we are examining the number of unsatisfied checks for each of them. So now if you see that this this bit has 2 unsatisfied check neighbors because this check is not satisfied, this check is not satisfied. All the other bits has like 1 unsatisfied check or 0 unsatisfied check. So now what you can do is you can flip this bit. So now again you recompute these checks. So essentially the flipping you can consider as a variable node update. And now again you're recomputing the syndromes that essentially you can consider the check node update. Now you see that there is basically again there are still some unsatisfied checks, and again you do the same procedure. See that which bits have more unsatisfied checks. Now if you see that this bit has 2 unsatisfied checks. All the other ones like have less than that basically. Now what you can do is you'll flip the leftmost bit. And then what you have here is essentially like if you see that all the syndromes are now satisfied. So this is a very crude example. So we take a very small graph, and what we are saying is how you want to flip the bits. You look at the equations and you receive those bits, and you would see that okay, this bit has like more equations complaining, so let me flip that bit. And now look at the equations again, try to see which equations are not satisfied, and again flip another bit. And in reality what we do is even when we are doing hard decision decoding, so in reality we flip because the graph is much larger. Let's say for instance for the hard disk drive, it's typically now it's a 64,000 bits. So it's a basically very large graph. So what you do is even if you want to do a hard decision bit flipping, you flip multiple bits at the same time because we're operating in a smaller graph here, but if you're operating at a larger graph, there could be multiple bits that you could flip in parallel.
Just a real quick question. What do you call that type of decoding?
This is a bit flipping decoder. This is a very crude decoder. This is not what we use. This to give an idea.
It's good to know the names.
Yes, yeah. This is essentially to give an idea in terms of how the iterative nature of the algorithm would work. So what we are saying is we put some constraints, and rather than trying to solve all those equations at the same time, we are solving part of the equations and trying to see what is the change, and then flipping another one. So let's say if you take a large graph of the LDPC code, let's say we start with the 91 errors. Once you do the second iteration, you may have like 50 errors. So and then next one 21, 10. So and then this one, the syndrome weight is essentially how many equations are unsatisfied. So in real decoding, if you don't have the, like it's in the simulation environment where you can see the number of bit errors because you know the transmitted data also. But in the reality, like when you transmitted something, you don't know what is really transmitted, then you have only the indication of the syndrome weight. Now when the syndrome weight reaches to 0, that's where you stop saying that okay, the received code word is most likely error free. But in the LDPC, what happens is there is a miscorrection also. So that probably is around 1 - 12 depending on the code length. Now what you have to do is you have to do another one CRC. You have to do a CRC on the top of that to make sure that there is no miscorrection. So if there is miscorrection, the miscorrection happens due to a trapping set. So again, you have to do different kind of post processing. So basically the idea is you're looking at the number of equations and then you see that how many number of equations are not satisfied. Until all the equations are satisfied, you're iterating that processing. And now what we did before is we simply looked at the number of unsatisfied checks and then flipping the bits, right? Now can we do better job, right? Instead of simply flipping a bit, can we make an informed decision? Because when I receive a bit 1 or 0, let's say if I'm sampling, say for instance a voltage from that is coming from the flash, I would have some reliability associated with that. Let's say if I'm reading a voltage instead of like if I'm reading a voltage of 2.5 volts, if my 1 is 2.5 volts, if I read 0.5 volts, that has less reliability as compared to if I'm reading a 2.4 volts. So now if I can get that reliability information, now if I can use that reliability information in the part of the decoding, then I can get better results. So that's what we call as a soft decoding. So what happens is like we compute a ratio called log likelihood ratio. So this ratio is nothing but there is a like ratio of two probabilities. For the case of the binary decoder, there is only one LLR. But if you take a non-binary decoder like of a GF4, usually LLR is a form of a vector. So you have three entries in the LLR vector, because for a GF4 you have 4 symbols. So if you take one symbol as a relative one, there are 3 more symbols that you need to compare. So essentially, the reason that again we choose the LLR is if you're dealing with the probabilities, you need to do some multiplication on those probabilities. What you're saying, if you have a logarithm, you need to do instead of doing a multiplication, you can convert into a addition. So that's one simplification in the computations. Let's say if you like one example would be is if I receive 2 bits in error, right? Now what is the probability of receiving 2 bits in error? That is essentially if those 2 bits are independent, then the probability of receiving both the 2 bits in errors are the probability of bit 1 and probability of bit 2. Now if I need to do that multiplication, that's more expensive in hardware. But what if I do a logarithm on the input domain? Then I have to do that that probability ratio, like a log of the bit 1 and log of the bit 2. So then it would become an addition. Now this the LLR is going to be available in most of the domains naturally, but in some domains, say for instance for the magnetic recording, based on the detector we compute a log likelihood ratio. But this happens once before starting all the iterations of the decoding, so that the LLR computation process is done one time before starting the decoding. Then once you are doing the decoding, all the decoding happens in the LLR domain. And this is one example. Say for instance, if I have a LLR of 100, so what it means is the probability of bit being 0 is 1, and if I have a like -100, that bit being 1 is most likely. So depending on the probability, you would get different LLR values. So what you have is instead of the probability, you have like a real number here. So you could choose to represent these values from -100 to 100 here, or we could choose to represent from -15 to 15. So if you do, let's say for instance, -16 to +15 or -15 to 15, you need less number of bits. So that's again like comes part of the fixed point optimization, how many bits you need for the decoder. And then in terms of the soft decoding, previously what we used is simply an unsatisfied checks to determine what bit to flip. So what we're doing now is instead of that, we have now all different kinds of messages. So one thing is what we received originally, that the message we get from the channel, and then what we have is for each bit, the easy way to understand this is the say for instance this bit is basically like telling to each check like whether it is reliable or not. So it has its own opinion about himself, about itself, and it communicates to the different check nodes. So now what it tells to the different check nodes could be different. It need not be the same. But once initially as part of the iteration, the information is the same. Let's say if I'm starting my first iteration, the what this bit tells to all these check nodes is the same information that it received from the channel. This channel information that could be from a detector or that could be from a demodulator, the how the initial bit has the like whether it's a 1 or 0, that reliability comes from the block before the decoder. And now once this bit sends this information to the different check nodes, what this check node does is it looks at all the connections it has, different bit nodes, and sees whether the check node is being satisfied or not. So let's say for instance if this check node is satisfied, then what it is going to send is it's going to send the information that's similar to what this bit node has sent. But let's say if the check node is not satisfied, what's going to happen is it's going to send contrary information. Like it is going to say that no, you're not 1, but you are probably like a 0. So essentially there has to be like when the code has to converge, there has to be an agreement between all the bit nodes and check nodes. And so usually what we do, this message passing is basically like passing the information between the bit nodes and check nodes is iterative in nature. So if you do say basically like the one iteration is essentially the what we call as the bit node processing, and the another is the check node processing. So I think there's more math in here, but basically the equation we use for the check node processing for the soft information is, let me show as an example here. Say for instance I received these 3 bits. So this bit is telling to this check node it is LLR is a -10. So what it is telling is it is a bit 1. So it's a sign magnitude, the 2's complement representation. So the negative sign represents it's a 1, and so it is telling that it is a bit 1 with a LLR of 10. And this bit is telling to this check that it is not that confident, but this is telling it's a bit 1 with a LLR of 5. And then this bit is more confident, saying that it is a bit 0 with a LLR of 13. And now this check node looks at all these ones and says that basically it sends back, it looks at all these 3, it says that okay, instead of it being -10, it says that okay, you cannot be this confident, you have to be only like 5. It ignores the -10, it takes the minimum of this -5 and 13, it looks at the absolute values and takes the minimum of that. So take the minimum of 5 and 13, that's 5, and then the sign it is going to send is essentially the sign of the exclusive OR of sign of these 2 signs, because the parity check has to be satisfied. So essentially the sign of this 1 ended up being the sign of these two messages. Now the same thing happens on this message also, RM2 to N2. So this one, what happens is you ignore this 5, whatever this bit node is telling to this one, you ignore it. That's an intrinsic information. So then you look at this -10 and 13, you look at the absolute values, that's 10 and 13, you take the minimum of that, so that's 10. And then again the sign value is computed based on the exclusive OR operation of these 2 different signs, minus and plus, so you got minus here. So the same thing we are doing here. So we're ignoring this 13 here, we're taking the minimum of this 10 and 5. So that's 5 here, and then minus into minus, that would be plus. So this is the check node processing.
Does that mean that M is a general processor? You're using numbers like -5 and +13?
Yeah, M is a check node processing unit. So this is essentially the M is let's say if I have like in the previous example I have 5 check nodes, that essentially there are 5 different check nodes here.
But that's actually doing multiplications and other complex. It's not just taking the.
No, it's just an edge actually. It's an edge in the graph. The computation is actually what is represented here. There are no more computations on the check node. The only computations are doing the minimum of the incoming values and selecting one of those values.
Is that equivalent to doing like a trellis decoding on a two-state code essentially, but you're just optimizing. I never quite because it's just a code, it's just a parity check code, which is accumulator. And you normally, when I think of that, I just soft decode it with the two-state trellis, with the BC.
Yeah, actually one thing let me explain. The LDPC decoding, you can do the decoding with a trellis.
Okay.
So you can do with the BCJR.
Okay.
And
but it's more I agree, it's more complicated.
Yes, yeah.
But this is essentially you're effectively doing that, but you've figured out I don't need to do all those.
Yes, yeah, exactly.
Add, compare, selects.
Yeah, exactly, yeah.
Okay.
The BCJR is more complex, so you actually, like, a lot of people try to do BCJR first, basically on the LDPC itself.
Right.
You don't need
that's where I'm at. So
yeah,
I'm
yeah.
trying to get where you're at, but I'm not there yet.
And so this is basically the check node processing. The variable node processing is actually simple. So remember the previous example I mentioned. So if I want to, for instance, if I want to compute the information I want to send to a specific check node, what I'm going to do is, this bit has, you can think of as several checks or monitors. So this check node is telling about this bit, and this check node is also telling about this bit. So each monitor or each check has an independent opinion about them. So now what you're going to do is, in order to make a total opinion, you're going to consider all of them. So you're going to consider essentially you're going to multiply all those probabilities. Since we are in the LLR domain, we're going to add up them, all of them. So that's essentially the total message that we are going to get. Give me 1 second here, whether I have it. Yeah, I think I probably moved that. Give me 1 second here. So that the total message is essentially the channel information plus all the messages that are coming for that bit from the different checks. So that's my total hard decision. And based on the sign of this, I'm going to say that whether it's a bit 1 or 0. And now the message I need to send to a different check node is essentially, I'm going to discount my own information. So what I'm going to do is, when I'm sending my variable node or bit node to the check node, I'm going to take the channel information. I'm going to take all the checks except the check that is directly connected to that bit. So basically, like, if I want to, if this bit is sending the information to this check, I'm going to discount whatever information I received from that. Essentially, we're discounting that intrinsic information. We take only the other information that is coming in. Similarly, when I want to send the information to this check, I'm going to discount this information, that R2 to 3, but I'm going to consider R0 to 3 and the channel information and so on. So variable node update is simply like a simple addition, but with the different probabilities. And the check node operation is a kind of a min sum operation. We're taking the min of the LLR. So the whole operation, what we're calling is a min sum, because we're doing the min on the check node and then the sum operations on the variable node. That's what we call as a min sum operation. And in terms of the parity check matrix, I think we're probably running out of time. I probably would just show some examples how the actual codes would be. This is one example of the array matrix. So essentially, you have the an identity matrix. And now in this one, the circulant size is 7, so you have 7 entries in the identity matrix. So all the first block row is all the identity matrix, and the second one is essentially shifted version of the identity matrix. The first one is the same identity matrix. This one is shifted by 1, and the other one is shifted by 2. This one is shifted by 3, and so on. So now in the third row, instead of being shifted by 1, it's this is still the identity matrix, the same as here. And the next one is shifted by 2 here. That's why you see 2 dots here. So essentially, what I'm saying here is you can construct an LDPC matrix using the circulants, and the way the shift coefficients are calculated using here is a simple formula for this one. But this code has a lot of weaknesses in terms of the error flow, so we don't use this code in practice. But this is a very simple example of how you can construct a code to get good waterfall performance. And then you could have a more complex construction. This is based on the cyclotomic cosets. There's more mathematical theory on that, how you arrive at these the shift coefficients. Because when you're constructing this graph, and what we want to do is we want to construct a graph without the a lot of loopholes in one sense. So we want to construct all the equations such that all the equations are giving if you do evaluate those equations, the decoding is going to be like a useful result. And in terms of the decoder architecture, one of the first ones that were done like by Agir, this is basically like LSI acquired Agir later. So what they've done is you have these computations on the graph. So what they have done is they essentially instantiated the entire graph in the chip. So you have these variable node unit. These are the like set of different editions, and then you have the check nodes. Those basically you're computing the check nodes. So what they have done at this point of time is they used a sum of products algorithm. They basically for the check node there are several algorithms you could use. One is the BCZR, another is the like sum of products where you do the log tan, and the min sum is one what I showed that's more simpler. And but at the same time the entire architecture they choose a check node architecture differently, and at the same time the way the architecture done is it's essentially like they instantiated the entire graph in the chip. So the chip area is around 52.5 square millimeter. This achieves around 1 Gbps. And later when we did the work, this after several years after this work, I think we are getting the similar throughput around 2 millimeter square or something on the same one, but it's a different architecture and it's a different algorithm, including both the check node update and in terms of how the decoding itself is done. So there's several changes. And one of the other initial ones are, okay, if the parallelization is complex, can we do just a serial one like as a processor approach? So we do one bit node operation and one check node operation. Now if you have, say for instance, if you have a 2000 bits and 1000 check nodes, so essentially you would have only one bit node on one check node, but you would do multiple. The bit node update takes around, let's say, 2000 cycles. This takes around 1000 cycles. While the bit node update is done, your check node is being idle, because you have to do one iteration completely. Iteration consists of all the bit updates and then the check node update. And so then another improvement is, okay, why don't we use a ping pong memory on here? Well, the problem with this, the memory is very huge. So if you're talking about a let's say even if you're talking about 10,000 bit code, the check node usually have edge of 36 values on each check node, and on the bit nodes you have around the column weight is around 4. That means you have 40,000 messages for the variable node messages. Similarly, you have roughly around 40,000 messages for the check node as well. So that means you are basically your complexity, number of messages you have to store in the memory are going to increase. So these memories are going to be more complex. At the same time, these memories are in the critical path again. And so now what you can do is you can do, instead of having one unit or all the units, you can have a trade-off in between. You can have instead of 10,000 units, or instead of just using one unit, can you use 100 units? Now when you're using 100 units, you're essentially doing kind of a folding operation. But how do you fold those operations? You cannot decide to arbitrarily like fold at different points, but the way you want to structure that could be different. Again, this is where like again tools didn't do good job again here. It's not like, okay, you can apply a folding transformation on the algorithm and it can give a good answer. So basically there are several semi-parallel architectures are proposed, and some of them are like basically like more in terms of the like they're still at a low throughput, and again they're more complex. And at the same time, they needed the huge amounts of memory. The reason they needed huge amounts of memory is when you're saying that, okay, I want to process 100 messages from this, the memory needs to have 100 ports, right? So now if you don't impose any structure on the code, then your memory is going to eat up, because having more ports to the memory is a killer. In reality, you really don't want to have, let's say, a random access memory with more than, like, even if you're doing a register file design, you don't have more than like 4 ports or something. So it's very complex if you're putting more ports on a memory. So that's one of the disadvantages in terms of the original ones. And at the same time, the interconnect design that was needed, because when you're doing these 100 ones, you have to do that graph, basically how those are connected. You have to do different interconnects. So those are also complex. So most of my work is basically in terms of what the concepts we call as a like on-the-fly computation is basically like we want to minimize the memory and the recomputations, and we want to do the computations as needed in time rather than trying to do the computation and then trying to store in the memory. And so one simple example would be in this one is, if you look at this one, there is when we looked at the this check node update, we are computing the minimum. We are ignoring this. Say, for if I want to compute this one, I'm ignoring this one. I'm computing the minimum of these two, right? So if I'm looking at a larger graph, let's say like which has 36 bits, I have to do this kind of operation. Like I need to find the minimum among 35 values 36 times. So now what we're saying is you don't need to do that, but you just need to find the first minimum and minimum two, and pretty much what you could see is here what you're getting result is the first minimum one and minimum two. So you don't need to do that minimum operation minimum of 35 inputs 36 times, but you need to do the minimum one and minimum two among 36 inputs one time, and then basically do that assignment here. So this is a transformation for this one. So previously the equation is you're taking the minimum among all these incoming values other than its own value, but now what we are saying is okay, take the minimum one among all these values and take the minimum two among all these values, and then assign those values depending on the index. So this is essentially a value reuse concept. And the hardware wise, it's pretty simple. You are essentially trying to find a minimum one and minimum two. As you're getting an input, you are essentially trying to find what is the current minimum one and minimum two. Let's say for feeding 36 inputs, after 36 clock cycles, you have a minimum one and minimum two here. So this is a very simple equation here. So it's basically like what you're doing is you are comparing with like you have two comparators, and let's say initially the minimum one and minimum two are like initialized to the infinite values. Now if a value comes in, and then if the value is less than this infinite value, let's say we initialize the infinite value as a plus 15 if you're talking with the if the decoder has a range of minus 15 to plus 15. Now if the incoming value is less than this, then you would put that value in this minimum one here. Now if the next value, say for instance, is less than the minimum one again, then you put it in min one, but the one you just replaced, you put it in the min two. So essentially you're doing a you're taking 36 numbers and you're looking at one number at a time, and then you're computing your partial min one and min two, and at the end of the 36 cycles you have the final min one min two. And now what you're doing is you're computing based on the output just from that min one min two. So previously what they were doing is you look at all these you look at the 36 inputs, and now you form different combinations like finding the minimum from those 35 values, find the minimum among those 35 values, and you repeat it 36 times. It's more complex. And then the variable node unit is where, again, like as I said, this is more of a like additions. So you're computing the p value using this equation, and then you are doing the removing its own message here. So I think probably I had to stop here. Give me 1 second here. Yeah. So I think another one I want to show quickly is you basically like what I showed is we are doing the computation on the entire H matrix. All the check node updates are done for the entire matrix, and then we are moving to the variable node update. But what if you do only partial portion of the H matrix? You do a check node update on that partial portion, but then you do the variable node update. So essentially what we do is like to improve the convergence, you do a partial processing and you update all the bit nodes. So in terms of the like one example I could show here is oops, okay. So one thing you can think of that, let's say if I do one check node update, I'm going to update all the bit nodes rather than waiting for all the other bit updates to happen. So I'm doing essentially like as a partial processing and updating my final results. So what it does is it improves the convergence. So what happens is instead of requiring, let's say for me 10 iterations, it needs 5 iterations. But now what happens is the hardware is much simpler. So let me show you this one. So for a non-layer decoding, that means if I'm doing on the entire H matrix, these are the 4 layers in the matrix. I have a hardware path for each layer. So now once I do all these layers, I'm doing my variable node update. So what I'm doing in the layer decoding is I'm doing only for one layer, and then I'm doing this variable node update again. And then after this one again, I come back here and then do this one. So what it is helping is instead of doing the 10 iterations, I can do 5 iterations. Now I'm having only only one portion of the hardware I need to implement. So essentially it's 1/4 of the hardware. And now what happens is I have instead of requiring 10 iterations, I need 5 iterations. Now there is in terms of iterations, I have 50% savings. So essentially for the same throughput, and I have to basically like spend off of the hardware resources. So that's what happens for the layer decoder. So what happens is you have only one CNU for one layer. There is a little bit more complexity would be added, but that complexity is more in terms of the control as opposed to the area. And then you do the different layers, and then you have the variable node update. So like essentially what you're doing is previously you're doing this check node update like the min sum as before, and then you're doing the p as before, the p and q messages. But what is happening is previously you're doing this r for all the layers, and then you're doing these equations. But now what we are doing is we're doing the r for one layer, and then immediately are doing these two equations. The advantage is you have a better convergence. And I can stop here. So then in terms of the turbo equation, this is for the magnetic recording. What you have is you have a detector and interleaver, and so now instead of what we are doing is you're putting a queuing on the input, on the intermediate values, and the output. So what we are doing is what packet has to be processed now. We are making a more like determination based on the packet quality metrics. The reason this helps is because here you need around more bits to store a data, but here in the hard decision queue you need only one bit for each because you have a hard decision. Here you have a soft information, so these memories are more expensive. So one simple idea is, if I have, let's say if I'm getting 100 packets, if I can process my best packets in the sense that it has less errors, then I need less memory in this one. That is the underlying concept on the queuing here. So you can do, previously we were doing the like around 2 global iterations, like 2 passes of detection followed by decoding, but with this one you can do up to 48 global iterations. So that means you can achieve the in terms of, say for instance, this example is if you are doing, say for instance, give me 1 second here. Oops. Oh, okay. Give me 1 second here. Yeah, probably let me explain this one. So basically, if you do like, say for instance, only one, say this one, the C is 1 and N is 12. That basically you have one processor and N is 12 is the buffering capacity you have, and the C is 1 and N is 1. You have one buffer here. So what we are saying here, if you have the queuing equal to the N is 12, then you can get the same performance as having the infinite processing. That means you having the infinite global iterations. So what we are saying is you don't need to increase your performance, but you need to have the queuing to get the same performance as infinite processing. The reason is it's the average. It has to deal with the average iteration. So if you have 100 packets, some packets need one global iteration. Now if you put in if your processing system is capable of on average of 2 iterations. Now if 99 packets take 1 iteration, then you are essentially accumulating capacity of 99 iterations. Now we can give these extra iteration to one failing packet. So now essentially you're getting a performance of a system with the maximum iterations of 100, even though you have an average iteration of 2. So essentially you're dealing with the average and peak, and then you're putting a queuing on top of it to get the performance. I think I will stop at this. So
There are any questions? We have about 5 minutes, 10 minutes for.
So in the layered, you're saying the layered approach, I get, so you're doing like a portion of the frame, and then you're taking the updated information, and then you're using that for the next portion of the frame, so you're kind of doing it like in chunks, right?
yeah, I think we are doing you can think of this way, like in the layer decoding, we are operating on the entire code word, but what we are doing is, let's say you have 1,000 check node equations. Now what I'm doing is I'm not updating all those 1,000 check node equations. I'm only updating 100 of them.
So you do 100.
Yes.
And then you update
all those 1,000 bits. Yeah.
And then you use those, wherever those 100 lie, you're putting them into the next 100.
Yeah. Yes. Yeah.
But I get how maybe that saves memory, because
that saves memory also.
Everything.
Yeah.
But then you're saying throughput I don't get, because it's just you're trading parallel for serial to me.
No, because okay, I see your point. Basically, like that's one thing. That's sometimes what we call as a layer decoding as a serial, and the non-layered as a flooding.
Right.
And but the advantage is because you are updating these, let's say 100 check nodes, and you're updating all these. Let's say you have 1000 bits or 2000 bits in the one. You're updating all those 2000 bits which are connected to this check node. Then what you're going to do is when you're updating the next 200 check nodes, you're looking at the already updated the bit node. So you're getting the latest information.
Better data.
Better estimates, basically.
Yeah.
It's essentially you can think of as an estimation improvement.
So you're saying it's decoding faster because you're using the new data.
New data, exactly,
earlier.
exactly. So you can do even though I showed the horizontal layer decoding, you can do vertical layered also, but that's more complex because you don't have the nice property of the min sum anymore. And that's another one basically. Yes.
I want to ask, just to get oriented, you're throwing around the number 1,000, just in terms of the original bits, this is a block code.
Yes, yeah.
But you do process the code iteratively.
Yes.
So it's a variable amount of time. But so you are breaking typically would you break up a bit stream into 1,000 bit segments?
Yeah, usually one concept we use is say for instance the hard disk drive, you have a sector of 512 bytes initially. Now we use the 4 kilobyte sectors, and now what is the LDPC code word size? That's up to you in terms of the design. Like we use, let's say for instance, less than 512 bytes initially for LDPC for lower complexity, and then we move to the 512 bytes. And 4 kilobytes you can have, for instance, a 512 byte code word itself, but you can interleave those 8 code words together to form a bigger code word. So the LDPC code word is independent of the sector size or the page size, but usually the preference would be is it's closer to the page size or sector size you want to write.
So the application you have in mind is reading a hard drive.
Yes, yeah.
When I think of error correction, I think of transmission.
Yes, in the wireless you can think of it because you have different packet size. Let's say even if in the 802.11n standard, we worked on actually most of my PhD work I worked on the wireless decoders for the 802.11n and WiMAX. So the packet sizes are different. So the packet size, say for instance for the WiMAX, it could go up to 2304 bits, and it could start all the way from around 300 bits or something. So the packet sizes are different. The rate also could be from 0.75 to like 0.8.
When you say the packet size, you don't mean what's going into a block.
Yeah, the packet is basically the block. Yeah, the packet is packet or the block are I'm using interchangeably. So in the wireless also you have different packet sizes, different block sizes.
The number you gave was 2,000.
Yeah, to the 2304 bits. Yeah, around 2000 bits. So what they do is depending on the channel condition, they go for the longer length and the lower rate.
And you had numbers that were more than 3-bit self-decision detection?
More than
3-bit self-decision detection?
oh, you're saying
numbers like -5, 13.
Okay. Those are basically like is basically what we're saying is that soft information you could use different bits. Say for instance, that example is for 5-bit decoder. That's usually the case what we use, 5-bit or 6-bit decoder. So the LLR, the representation.
You say 5-bit decoder. You don't mean 5 bits to represent each bit that you read.
No, you need 5 bits to. So essentially, when you read a bit, yeah. Yes. So when you read a bit, you can do a hard decision that's either 1 or 0. But now what we are doing is we are assigning a probability whether that bit is 1 or 0 using some soft information. That is essentially a probability. So that probability we are representing, like in the actual floating point simulation, that's an infinite number. That basically like a floating, single floating, or double floating. But when we do a fixed point, it's usually 5 bits or 6 bits.
So when they're reading off the disk.
Yes, that number what we get is from the detector branch metric. We calculate that LLR.
And that the processor was simply that you had to going back to that orange processor was just taking the minimum of all the numbers. The numbers itself that we care about is where.
Yeah, we're taking the minimum among the absolute values, and then again when we're computing the output for a check node, based on there is a simple equation, the whether like once we compute the min 1 and min 2, we are assigning that min 1, min 2 to the outputs. So most of the outputs would have the min 1 as the output. Only one thing would have the min 2 as the output.
But these are very short. So he's reading short. It's a big packet, but it's made up of small codes, right?
I thought it's 1,000.
No. It's
all in a big.
No.
That matrix, that H matrix.
Right, but the H matrix represents 1,000 little teeny codes. This is a low density parity check code. It's like 1,000 small 8 to 10 to 16 bit parity codes, right? So he takes those, he decodes each one individually, these little short checks, and that's where he gets the minimum. For every one of those codes, he calculates a minimum and a second minimum. And then based on that, he feeds back to the 8 bits or 16 bits in that code what he thinks they should be. And then they go to their other code. They're each in about 3, 4, 5, 6 codes. Those go to the other codes, and they tell them what they think they should be, and then they send them back again. And he does that 50, 60 times, and you figure out what it is. Believe that's what they do. That's what they do.
But you have to live with it a little bit to follow that.
Kiran, please let me know if we can post these.
Yes, you can post them. Yeah.
We'll put them on the website.
Yes. So there are a lot of backup slides. I think basically what I've done is I moved some of these slides from the original place to the backup slides. They may not be in order. So what I can do is probably you can post them, or probably what I can do is I can put them in order and you can put them whichever.
Arrange it the way you want, and then I'll.
Okay. Yeah, I can arrange them in order and then you can post.
Thank you very much.
Okay, sure. Yeah, thank you. It's nice talking to you.
It's almost like going down to square zero.
That addresses issues that are at a lower level